questions on project stuff, we can do that. And then I've got a bunch of review materials just to review for the whole semester. Okay, so this is actually a study from a friend of mine in Germany. Which is moving from efficacy to effectiveness in cognitive behavioral therapy for psychosis, a randomized clinical practice trial. Randomized controlled trials have attested to the efficacy of CBT in reducing psychotic symptoms. Now studies are needed to investigate the effectiveness in routine clinical treatment, routine clinical practice settings. 80 patients with schizophrenia spectrum disorders who were seeking outpatient treatment were randomized to a specialized CBT intervention for psychosis or a wait list. They were assessed at baseline, post-treatment, and 1-year follow-up. The wait list was assessed at baseline, 4-month waiting period, post-treatment, after 1 year. So, same thing. Primary outcome was the positive and negative syndrome scale, the PANSS. Now, first question is, before they started, they wanted to assure that the two groups were equivalent on gender. So that's the first one. How do they decide if the two groups are equivalent on gender? 40 per group. There were 22 out of it, 22 males, 18 females in the CBT group, 23 males, and 17 females in the waitlist group. How would they decide if they're equivalent? That's question number one. I'm going to do a bunch of them just so we have a review.
How did they say equivalent? Then how did they decide?
Yeah, what statistics should they use to decide if the groups are equivalent in gender? Pre, post, and 1 year later on the PANSS positive, PANS negative, PANSSGP, PDI distress, PDI preoccupation, PDI conviction, SCLGSI, the BDI, the CDSS, the GAF, etc. So they give all those measures they gave everybody at pre, post, and then at 1 year. No gender. Just the wait list versus the active treatment group. They're comparing the wait list to the active treatment group pre, post, and 1 year follow-up.
And they're not really looking concentrate.
More than the last one. I played my Grease table this semester. I will soundbite from Grease telling me more, telling me more. There it is.
We don't really have a conflict, but
It's fine. Second one, a little better.
I see you through the day.
Stars in the line today.
What?
I don't think there are stars in the line
There's
today. There's a lot of others missing too. There's just weird traffic and everything. It's very weird today.
Perfect storm.
Something going on at Miramar, I think, because it's giant going up to into the base of the time that they don't see it. They call it calm. Stand down or something.
It's taking 15 minutes to get to the freeway, normally it takes me 6.
Where?
Just from my house.
Where is that?
Boswell.
Oh,
How long is that from?
Like 40 minutes, but
a little long.
we'll get out of the way and sooner.
That's important.
Okay, so the first one, most of you got, is category data and chi-square, right? So there's one DV, gender. You can do it two different ways. You can say there's two DVs and no IVs, gender and group. You can say there's one DV, gender, one IV, group. But what kind of data is the group, is the gender, is category data, so that's chi-square. So those category ones are always going to be chi-square for those. Age is a continuous measure, so you've got one DV age, one IV group. They're not compared to each other. I mean, they're not compared to themselves, they're compared to each other, so it's an independent samples t-test. When there's two different groups, it's independent samples. If they're comparing it to a normative value, then it's a single sample. It's the only time that'll ever be a single sample if we compare it to a normative value, and if it's compared to people compared to each other, then it would be a paired t-test. So in these kind of group equivalents, it'll never be paired t-tests. And then the last one was two IV, a bunch of DVs, two IVs, group and time. Group is between group, time is within group. So it's a two-way MANOVA with one repeated measure. All right, so here's a whole bunch of other group equivalences they did. We'll do a group equivalence to start with. What do they do to that one?
We're doing another one right now?
No, we're just practicing.
Yeah.
So we're going to go through a whole bunch of other measures that they wanted to check for equivalence at the beginning. So marital status, or family status, they call it. Which one? How do you do that? Chi-square, because it's category, good. Years of education. T-test, it's continuous, good. Education final level, which is none, low, medium, or high. That's back to a chi-square they did. They could do that one different ways. It's chi-square. Premorbid. Rank, remember, rank is only if they put them into first place, second place, third place. People ranking themselves is not rank.
Okay.
It has to be ranked with compared to one another. So it should be, I shouldn't be able to fool you on rank. It has to be I have to make it very clear to make it obvious. So in that case, if it's some rank, it'll be, researchers weren't able to do score data, so they ranked everybody from the highest to the lowest to the highest. Premorbid verbal IQ. T-test. Main diagnosis, whether it's schizophrenia, schizoaffective, delusional, or acute. Chi-square. Patients with comorbid, axis 1, chi-square, yes or no. Axis 2, yes or no, chi-square. Patients with not on medications, yes or no, chi-square. Years of psychosis. T-test. So all these are not significant, which is good, right? You want the groups to be equivalent to start with. Then they did the MANOVA, and they did find good results on most of those measures, actually amazingly good results, with effect sizes of between 0.77. What kind of effect size is that?
Large. Oh, wait.
0.77, I guess that is, no, 0.8 or more is large, isn't it? 0.8 on, but is it an omega squared, an eta squared, or a Cohen's d? A 0.77, what do you think? If it's an omega squared, that would mean 77% of the variance is accounted for by which group they're in. That would be very large. So it's not. It's a Cohen's d. Most effect sizes are reported in Cohen's d. So that means that the one group on the PANIS GP, whatever that is, the PANIS. It's not the PANIS. It's the PANSS. It's not the usual PANIS scale. I don't know what GP is, general something, but general psychopathology scale. That was the one that was 0.77. So that would mean that the group that got the CBT was 0.77 standard deviations above the group in the wait list, which is pretty good for psychotic symptoms, really. They also did it with that was pre-treatment to post-treatment, and they did the same thing from pre-treatment to 1 year follow-up, and got a 0.82. So that means the effect size, both of them were significant, but the effect size continued to increase over the course of 1 year after treatment, which is awfully encouraging, I think.
How can their effect size increase being on waiting list?
Because the treatment group got better compared to the waiting list.
Oh, I see what you
Well, actually, this one is just for the effect. This is just the treatment group. How much did they improve, not compared to the waiting list? So they did that in another place. So anyway, you can kind of see the idea of it. Effect size, adjustments will be excluded. Then they did it for a bunch of different effect sizes for different, if they had low IQs, what would be the effect size? If they had schizoaffective or if they're delusional or not. They had no actual psychotic symptoms. Pretty impressive study. Okay. So let's see, what else do we need to go over on the decision tree? Seems to me that people have the hardest time with those ones we just did. Usually, everybody's getting the ANOVAs, repeated measures ANOVAs, the MANOVAs. You gotta tell me how many repeated measures and how many levels. I take points off if you don't tell me how, somewhere in there. If you do your little IV chart and you tell me there's 2 levels and 3 levels, that's okay. But if you tell me it's a 2x3, that's okay. You gotta tell me. And if you say just MANOVA, then you're gonna get points off. You gotta tell me MANOVA with or without repeated measures. I think we're pretty clear on logistic versus regression now, right? It's just depending on the outcome. Don't worry about the predictors, right? The predictors could be any kind of data. It's only the outcome data in regression that matters. We went through the 3 t-tests. Can anybody think of an example of a single sample t-test?
I want to find out if there's more cancer with people that live around power lines, so I can get a sample of people that live around power lines and compare it to the population.
It's basically good. There's one little problem with that. What is your data going to be like for that? It's either category, right? It's going to be a percentage of the population, right? So that's a little different. That is the right idea of the single sample compared to the norms, but in this case, you're looking at risk. Yeah, you could do lifespan. Yeah, you could do lifespan. So if you said, let's look at the lifespan of people living around power lines versus people who don't live around power lines, then you get the norm, the national norm of longevity for the actuarial statistics or something versus some people living around power lines. Or let's say we wanted to see how our graduates do on the national licensing exam versus the norm for that year for the country. So we would look at and say that our guys. Yeah, it's hard to do it because you're competing with places like Berkeley that have 3 graduates taking the exam versus CSVP, which have like 19. So if we compare ourselves to other good-sized schools, the 2 PhD programs, Berkeley and the 2 of the 3, Berkeley and us do really well. LA is not quite as good on the PhD. The PsyDs are a little worse all across the board. Not much, but just a little worse. But generally, all CSVP grads are better than other professional schools, but not as good as research universities. But those are hard to gauge. The joint program, the UCSD joint program, they usually have 2 or 3 a year taking the license exam. And they're really smart kids, and the license exam for them is a piece of cake, so they almost always pass it. So, you're going to get very elite programs like that. It's going to be hard to compare to. Anyway. What other parts of the decision tree? Anybody see any parts that we're going over?
What are the paired t-tests?
Oh, paired t-tests. Okay, so that's where you have people compared to themselves or to a matched sample. So, and if you just wanted to do, let's say within this study we just did, you wanted to just compare pre-treatment to 1-year follow-up for just the CBT folks, right? Nothing to do with the controls. So now you got 2 groups of people being compared to themselves, right? So 1 DV, 2 levels, but they're compared to themselves, not others. So that would be a paired t-test.
I don't see ANCOVA or ANCOVA on here.
Yeah, we
kind of know to do that.
Yeah.
So
Usually it's just like you do with the same model with the covariate or not. So you put a C in there if there's a covariate. There's really nothing. In order to do it, you could say, you could put in there, are there covariates? If so, ANCOVA. If so, MANCOVA, if you wanted to do that. But if I were to give you that as a decision tree, it would be pretty obvious. I'd say if you want to control for something, a hold constant something. So we just didn't have room to put everything on there. We can put that one on. What else? The non-parametrics we don't really cover very often. They come up so seldom which would be rank data usually, the same model as the ANOVAs with rank, or a t-test with rank data. So if you look at the decision tree, there's a non-parametric equivalent to a one-way ANOVA with no repeated measures, a one-way ANOVA with repeated measures, and it would just be under the rank data category. I'll just look down to, let's say, one-way ANOVA with no repeated measures, find that one.
Yep.
Okay, now look at the rank data equivalent of that instead of Kruskal-Wallis. So Kruskal-Wallis is the same exact test, but it's done with ranks. And it used to be common because people had normality issues. They say if you violate assumptions, one way around it is change everybody to a rank. Then you can't worry about outliers, right? The first place is first place is first place. You can't have an outlier. So you can change everything to ranks, including ties, and then you can compare them in ranks. And so it's a pretty simple test. If the control group had lower ranks overall than the experimental group, then they end up not being significant. But of course, you lose a lot of power. And so it's not real common to do those. But it should be easy to spot. If you get to the spot where you say, well, I would think it's a one-way ANOVA with no repeated measures, but it seems like it's ordinal data, ranked data. Not people ranking themselves on a 1 to 7 scale, right? Don't be fooled by that. People rank with regard to one another. Dog show data. First place, second place, third place.
So like if you wanted to maybe if you wanted to see people who are the same by education, but because that can mean so many different things, you're like, okay, we're just going to go with, you either have a high school diploma, you have a college degree, or you have beyond, you have coaching.
And we probably would call that category.
That's the category.
Because you can't really rank, see, you can rank people 1 through 3 themselves, but that's not the ranked data really. So we wouldn't have any more ability to rank them. I mean, maybe we could, based on something. The judges could look at their education and rank them from most educated to least educated, but otherwise you wouldn't bother with that. You would just use category. Even if there is some order connected to it, if there's only 3 categories, you probably need to use category data.
Could be more like this, they use like GPA to rank.
Yeah, so you could say, or like your high school rank, there's rank data. Right, so if we were comparing people within the same school on rank, right? So let's say we want to look at the difference between people who took AP classes in high school, for those who didn't. We could look at their class ranks compared to one another. Now we're getting their actual comparative ranks. We'd expect the people taking the AP classes to have the higher ranks than the ones not.
That's because they have like a 4.5 GPA.
Exactly, yeah. Yeah, but you can also do it by GPA too. But in this case, if you thought, that would be a good reason to do it that way, because schools that offer a lot of AP courses and teach to the test, right, make everybody gets A's in those AP classes, or a lot of people get A's in these AP classes, so they get these inflated grade points above 4. And the colleges have a tough time deciding what does that actually mean. So it might be better to look, so then you get complications, because if it's an elite school, then the rank within that school might mean more than it would if it's a inner city school. But if you come out in an inner city school with a high rank in your class, you've got a good chance of getting admitted to a good school, even if your grade point isn't a 4.7 or something. There's this new movie out, Admissions, with Tina Fey, where they really did, it's not a great movie, but they really captured the admissions process from Princeton. She's at Princeton. I think that is right on the button. What you saw there, I think somebody was an insider on an Ivy League school admissions, because every little thing they did, the territories, how they play politics with each other. I know somebody who did that, and that's, so in this case, she's got a favorite candidate she wants in, who doesn't quite meet up because he had lousy grades in his first 4 years, and she tries to make a deal with another admissions counselor. I'll let your favorite in if you let my favorite in. That actually happens. I mean, these are all highly qualified kids that go to Princeton, obviously, so it's a fine grain. Admissions.
Yeah.
Admissions. Tina Fey, Paul Rudd.
Oh,
Was-
wow.
Wasn't a great movie.
It's too bad because I
Wait
love
for
this
it to
Paul
come out.
Rudd.
I'm just kidding.
It's too bad what?
It's too bad because I love Paul Rudd.
Yeah.
Oh, you don't like Tina Fey?
Oh, I like
Oh.
her too, but
Oh, she's good, she's good. It's just not, they couldn't decide if they wanted to make it a comedy or romantic one. So there were some funny parts. Lily Tomlin's in it, she's very funny.
Yeah.
But there was a lot of not funny parts. I don't know, it was okay. We were in a desperate mood for a lighthearted moment, we went to see that one. It was probably stupid.
Did you know what storyline is?
I never had the sleep, no sleep too much. I'm sure it's great, but you really need
I was
that.
curious, I haven't had
Need to be
anybody
well
that
rested.
watched that movie.
Storyline.
It's heavy,
It
heavy.
is very heavy.
I'm sure if you're in the right frame of mind. But I've sort of learned my lesson, especially when I go to England. I go often to England, and there's such great theater there that I would always try to find something to watch. Well, you'd be the second night you'd be jet lagged, and unless it was some really light comedy like the $1 Million Quartet, that one kept me awake for sure. But like a Strindberg play or some heavy-duty national play that's it's really spending one time of money.
Read Crown Mountain.
Okay, anything else on decision tree? Should go over?
There's one of them,
Otelling's T is just the T-test equivalent for Manova. So whenever you have the same thing as but if you put down one-way ANOVA with no repeated measures, I'll give you credit anyway. So some people put down for the T-test a one-way ANOVA, no repeated measures. It gives you an F, which is exact equivalent to the T. So you get exactly the right answer. Probably should know that when there's only 2 levels, you should use T-tests. So the Hotelling's T is a special case of ANOVA when there's only 2 levels of the item. Okay, let's look at a couple things first here. And we'll start doing some review. Here's a,
I was looking at a thing of abbreviations back to the APA manual, and there was 2P's very significant something test. Is that the same as 2P's?
yeah, least significant difference, LSD. Well, there's about 4 different 2P tests, actually.
Okay. So it was one that was like very significant, blah, blah, blah.
Yeah, no, those are just slight variations of the same thing.
Okay.
See here?
yeah.
She drops. You wait for her?
No.
Oh, Christina, wait. Do we know who she is? No? All right, so this one, I'll go over in a minute. This is just showing you, the site starts. Sorry. Repeated measures Manova. It's a little tricky to do it. You don't really have to do it on the project, but someday you may need to do it. And then I also have Mancova in here too. And this will be a good review of, we can go through that and that'll be a good review of Manova. One trick on Manova that we didn't go over that you might need for the project actually is how to do plan comparisons if you have more than 2 groups. Right? So you do have 3 groups in your Manova on that project. So if you wanted to compare any particular combination of those groups, it's sort of tricky to do in Manova, but here's what you have to do. I'll just put an example here. I don't know if we actually looked at this example before, but this is the one where this 1960s one where women were divided into 4 categories: high masculine, high feminine, androgynous, or non-differentiated, based on the BEM sex role inventory. So we're going to just a big sample we can compare. So we're going to have the 4 group, and we're going to compare those 4 groups on a bunch of DVs: locus of control, socioeconomic, introversion, extroversion, eroticism. Right?
Do you have that on our handout?
No, we don't have this one. I'm just going to show you one trick on this one, just in case you want to. You might need to do this, and you won't know until last minute probably. So the standard part of it is easy. You just do the MANOVA. You put your DVs in. And this is the fixed factor IV, the 4 groups. Use our usual options. And you should do sum of squares and cross products too. I won't bother for this one. We're not going to look at that right now. And you could put plots in to see what the graphs look like. I won't bother with that. But here, there is this contrast button that we haven't used in general linear model before. But there is a way you can use it for MANOVA. Remember, if we're doing comparisons on a single DV, we do it with the means module, where we do put the 1, minus 1, 0, 0, like we did first semester. But you can't really do that if you have multiple DVs. So there is an opportunity to do that, but you have to kind of be clever about it. You can choose a contrast, and these are all different set contrasts. But the one we want to probably do is just the simple contrast. And then it says it's going to compare the first or last group to the other groups. You can choose it's either first or last. See what I mean? So it's going to use the factor, the 4 categories. And now in this one, our first category was high masculine, so it'll compare high masculine to the other 3 one at a time. So you could switch your groups around if you wanted to make them work that way. So that way, and then you click change, then continue, and then OK. Then it gives you, along with the MANOVA, a pretty elaborate set of contrasts. The trouble is you can't do 1 and 2 versus 3, or 1 and 3 versus 4. To do that, you actually have to put in different coding of the groups to actually combine those groups with the coding, right? Yeah, so you just either just use those. Let's say you wanted to combine group 1 and group 2. You go in and put your coding in, so everybody in group 1 and 2 is in one group, right? You give them all 1s, and compare that to group 2, and that'll be the combination of the 2 versus the other one. That kind of works. It's unfortunate that SPSS doesn't have the contrast, but all right, so there's the basic output, and then it says custom hypothesis tests, level 1 versus 4, level 2 versus 4, level 3 versus 4. So that gave us those contrasts. For each DV, it gives you the hypothesized value, the difference, and the 95% confidence interval. Just can look at the significance level. Clearly 1 was significant from 4 for except not for attitude towards the role of women, but the other ones are well significant. Here you can look at level 2 versus 4 and level 3 versus 4. Now if you switch that around to the first versus the last, then it changes, you can change it around the way you do it. And then it gives you multivariate results of, let's see, this is, so here's the 4 groups. So there's 4 groups. So look at the Pillais 327. Here it gives you, yeah, it's the same thing. I don't know why it repeats that. It just repeats the same ANOVA, but that doesn't tell you anything different. There's the univariate test. Those are just the group means. Okay.
I have a quick question while you're on the Manova. When you go into run the Manova and you need to change the model from the default to custom.
To run Manova? No, you don't. The only one time we do that is to check assumptions on Ankova or Mankova.
Okay.
So the reason you're thinking of is because we did a Mankova that way, just to check the assumptions of the Mankova.
Okay, but when you're doing that in SPSS to get the interaction, to get the two IDs to be times each other, I'm having trouble figuring out.
Okay, so let's do this one. Let's put a covariate in. That's what we'll need to do it, right? So we'll do multivariate, but this time I'll put attitude towards the role of women as a covariate. Okay, so that's the only time you'd have to do that is when there's a covariate. So then you're going to do model, custom. Now you do the two, the IV and the CV, right? IV, CV, and then just highlight them both. Put the IV times the CV. I think you can do it with this interaction button too. I
I was
can't
trying to do that and wasn't working.
remember. I forgot the trick to that one, but this is a good way to do it. And when you say continue, the output that you care about there, remember, is only this interaction. Look at the multivariate interaction here, and if it's not significant, you're good. If it's significant, you could look at the univariate interactions to see where the problem's coming from. Anything else from the project? Okay, let's look at this repeated measures one, if I remember what I did it on. So to do repeated measures of MANOVA is a little non-intuitive. And I can't remember what I did this one on, education meds. Okay, so we get a new file. Data. This should be some Robbins data. Well, I wonder if I didn't put that in my thumb drive.
So Bert, some quick questions of paper for the project, not related to NOVA, but when you have the structured matrix, you're looking at like factor values. If they're high but they're negative, would they still load with a positive high? Would they end up with
Just bipolar, it just goes in the opposite direction, that means.
Okay.
So yeah, big negative ones are just as meaningful as big positive ones. You just have to use them in the opposite. So they could be,
So if it goes negatively on something.
it could be positive affect to negative affect, or it could just be the amount of positive affect 0 to something, right? So some factors don't have any negatives. Then they're just kind of unipolar. They go from 0 to something kind of. Some of them actually have have bipolar kinds of meaning. So big negatives are definitely meaningful.
Okay. I think we were having trouble trying to figure out what to like name
It's
them because
always-
they're
It's always hard.
pretty.
It's always hard. And it's a good thing to remember when you look at published literature, see what they name those factors and look at the loadings. And you may be very puzzled on how they came up with that name. The 16PF is totally baffling. Suckerance is one of the factors. There's a whole bunch of them on the 16PF that I'm thinking, really? Where did you get that one from? I don't think I put this data in my thumb drive. I'm gonna have to figure out something here. Let's see. Maybe I got it. We could just do it, I suppose, with the, maybe I've got one here that'll work. It's not going to work because we only have one DV. Darn it. All right, we'll just do it out here. So this was, I believe this was our yoga study, I think. So, so we've got basically a whole bunch of measures for fibromyalgia. We have pre and post for a yoga group versus a weightless control. Okay, so it's a 2 aim novo, 1 repeated measure. There's a whole bunch of measures. So the measures are the PSQ, the AIMS. AIMS is an anxiety scale, the PSQ is a sleep scale. CST, you know, is a depression scale. Then there's some heart rate variability measures too. We'll see which ones they use. So you go into for ANOVA for this one. You don't go into multivariate. That's the first thing that's not intuitive. Right, don't go to the multivariate down menu. You go to the repeated measures menu. You see it over here? And you put your repeated measure in, which is going to be time for us here. And it has 2 levels, pre and post. Then in that little section below, if you've never used it, you actually name the DVs. So the fibromyalgia impact scale, the fibromyalgia, what is it, an FIQ? Can I read that? I don't know. Whatever. It's another fibromyalgia scale. The Waller functional scale is a function 1. The AIMS is anxiety. PSQI is sleep. Okay, so we got our 5 different DVs down there. Then you'll see what happens when you turn the page is it gives you a menu to fill in all of the pre and posts. 1 is pre, 2 is posts for all of those different measures. So you got to kind of remember which ones you put in where. And then you just drag them over. FIA1, FIA2, FIQ1, FIQ2, so where I'm pointing here. And it'll only let you put in the right ones if you set it up right. Then you put your group in the between group. It's good to remember covariates don't really work in repeated measures. It only covariates it out of the first level of the repeated measure. So you've got to think about something else to do if you want to do ANCOVAs with repeated measures. It doesn't really work very well. Okay, so then here's what the output looks like. It's actually not going to be too puzzling. It's going to look normal to you. So here's the multivariate repeated measure time. There's the time by group, the interaction. And that's just the rest of the data for that. And then it gives you the univariate tests. Remember, use the Hunfeld correction always. So we have to worry about using. So it gives you whether there's a time effect for, this is just time, so that means both groups improved on the FIA, both groups improved on the FIQ, et cetera, et cetera. Then the next page shows you the interaction, the important one, no, not yet. Page 9, page 10 shows you the interaction, I guess, yep. So go to page 10, so now that's the important part. We look at the Hunfelds for the interactions. It just kind of carries over to the significance on the next page. So we can see we actually got it on sleep. That is, one group improved more than the other group on sleep. You can see the PSQI on page 11 now. Just looking at the significance levels, page 11, right next to it. The FIQ is close to a significant interaction. The Ames, none. The FIA, none. So the interaction means that the control group improved differentially from the actual treatment group. And we can see where that came from. The multivariate interaction, did we look at that before? We should have looked earlier at the multivariate interaction. I told you that. Let's see. Group of time. Variance.
Control group improved differentially with the main group.
Then the yoga group. See, where's the? We go to page, instead of time by group, actually have to look at page 4 to get it, unfortunately, because it carries over. And you can see the multivariate interaction was not significant. I should have probably written that on there for you. Page 4, time by group, been felt is, the multivariate significance even for Roy's is 0.196. So that means that for the DVs as a whole, the Roy's, remember, is just the first variant. So it just does it on the first factor of all those DVs. That there was no differential between the controls and the yoga group when you put all the DVs together as one combined variant. Losing it?
Yeah, where's, I don't
See the page 4, bottom, 0.19, I'm looking at the significance level, 0.196 for Roy's largest root. Everybody find it?
196.
0.196, so just looking at the significance level.
Yeah.
So that's not significant. So that would tell us that for the first variant, principal component factor, whatever you want to call it, of those 5 DVs, we did not get a differential effect from yoga to the controls. So now if you decide to go ahead and look at the univariates, which we just did, and we found that especially the sleep scale was significant. So are you allowed to interpret that or not? So maybe, now we're page 11 again.
So you want the Roy's to be significant?
Yeah, you'd like the Roy's to be significant. That would mean that you've got overall the measures as a whole differentiated the two groups. The 5 DVs as like a factor would have differentiated between yogas and controls.
When do we look at lambda compared to the way where it's
Well, any of the other ones you can look at if you want to look at all the variants, not just the first one.
Okay, so
But if
what
you-
are the only first?
Just the first, that's unique because it's only the first variant. So it is more powerful. You'll get, the first variant will be the best, like the best principal component. It'll do its best to find that. So once it finds that, then it's going to do it in that one. And oftentimes that's the only one you want to interpret anyway. Now in the fields when we looked at last week, there were 2 of those that made sense, right? One was kind of the bipolar one was the single polar one. So sometimes you want to use all of them. It just depends on what you care about. Question, Heather? No. So now the question is, could you interpret that 0.031? If we use the strict Bonferroni, you would divide 0.05 by 5, because we got 5 DVs, and that would have to be a 0.01 to be significant. So it wouldn't make it.
Where's the point of the one?
It's circled on page 11.
So if the overall
Yes.
treatment wasn't significant, could you only really say that the one treatment?
Well, that's the thing. So then you could say, well, I'm going to switch from a multivariate strategy to a univariate strategy. But if I do that, then I've got to deal with type 1 error. All right, so that's when we go back to that complicated Hummel-Sligo graph. or we'd have to figure out what the correlations are between the 5 dBs, get the averages of those to get the percentage of variance in common. Look and see what our sample size is and how many dBs we have. So we have 5, so we'd have to use the 6. Remember in that chart from last time? We'd look at 6. Let's say it was 30% variance in common. We'd look at how inflated the alpha is in that top chart. And it probably we can get away without having to use a strict Bonferroni of 0.05 divided by 5. And whether it would make it a 0.031, I can't remember when we really did this or not. Make sense? It's a little complicated to do it that way. Or if you want to be more conservative, you just say, nope, I'm not allowed to interpret that as sleep difference because it was only 1 of 5 and it could have been just due to chance. In this case, we were desperate to find a good finding in favor of yoga, and the sleep was much better, so we worked it around to be able to report that. Yeah, this is real good. 12, 13, I don't think there's anything else there we need to look at. 13, is it 14? Remember this table here, I just put it in there to remind you to not look at the trend analysis unless you're actually doing a trend analysis. On page 14, top, tested within subject contrasts, linear. It looks at the linear contrast for all of these. You can only use those if you've got a quantitative IV. Doesn't really work for this one. So I just said ignore on there just to remind you. Levine's test, you can see we had some violations of homogeneity, but they were fairly slight. So we have homogeneity violations that are not super significant. Look at the F-max. See if you can get away without worrying about it. Remember the sheet I gave you last time, if there's reasonably good sample size and reasonably equal sample size, you can pretty much ignore minor violations of homogeneity. We don't want Levine's to be significant. Between subject effects would just be if we're not caring about time 1 and time 2, so they'd be pretty meaningless here. Those look like the groups didn't differ from each other overall, which doesn't really mean much of anything if you have a repeated measure. 16, 17 we don't care about. Okay, then here, the next one is the Mankova results.
16 and 17.
Now we're up to page 1 again under Mankova, 16 and 17 we don't care about. There's nothing there we need to look at now. So just to give you an output from a Mankova, what did we do here? We did biofeedback exercise and control. This is Dr. Beltran's dissertation for the health students. So she did a biofeedback for fibromyalgia patients. She did biofeedback. She did a pool exercise condition and a control condition, just treated as usual. And she had more subjects than the original one, but this data just had this. So we can see the multivariate tests here. Now in this case what I did is I just turned these to a single score. See how it says delta on the side? Those are all improvement on these scales. All right, so we don't have repeated measures here, just a Mankova on how much they improved. So we can see that the delta, so in this case there's 1 dV, which is the, whoops, no, it should have been more than 1 dV. Delta CEST, I must have labeled that wrong. Oh no, the CEST was the covariate, that's right. Okay, so we do controlling for depression. We're looking at how much they improved on those other measures, on the PSQ and so on and so forth. So here we're looking at, was the covariate significant? And it was. See the .01s there at the multivariate level. So we do get a significant covariate, so it might be worth using. However, we did not get a group effect, so we're not going to have to worry about too much more. But for the Roys, it was .110. It might have been a trend with small sample size.
If you box the edges, it's significant, that's good.
And that's good. The box system is not significant, that's good. I mean, you probably don't have to worry about assumptions very much. Then we have the univariate tests again, saying that we're going to get the same basic results as before. PSQI, where are you? Got to go to 16, 17, 18. Here's 17. Stapled in a weird way there. Something wrong here? Am I not seeing 18? Are you guys finding 18? Or maybe I didn't print out the right stuff here. So the rest of the output would be just the testing the assumption, but don't have to worry about it so much since we didn't get group difference anyway. Sorry, I guess I should have gone, I don't know why I didn't print out the rest of that. Oh yeah, there it is. So it's 1450 for some reason. No, that's the same as before. Okay, so I just did the rest of the thing. I just wanted to show you a little bit of that. Okay. So what I did was I compiled all the concept lists into one. Dropped to the floor. So you've got all these actually, but this way we've got it in one place. So as we're going through these different units, check your concept list. See if there's any concepts we especially need to go over. What I'll do is just go over the output. The review is I made up. This is actually the book we're going to use next semester. Tell me, remember we used a few things from this book.
Wait a second, just a You're getting a step length.
Oh, well, oh gosh. Yeah. Just realized I got a message that I shouldn't have taken. So just as a, take some new data we haven't looked at that actually has some problems on it from Andy Field's book. So, this first one is for regression. So I just got these whimsical examples that I use, so I thought we'd do that. So, fashion student was interested in factors that predicted the salaries of catwalk models. She collected data from 231 models. Each model, she asked them their salary per day on days when they were working. That's called salary, their age, how many years they had worked as a model. Then they got a panel of experts from modeling agencies to rate the attractiveness of each model as a percentage of 100% being perfectly attractive, beauty. Uploaded the data is in a file. Unfortunately, the fashion student brought some substandard statistic text, and so doesn't know how to analyze her data. Can you help her out by conducting a multiple regression to see which factors it should be predict the model's salary and how valid is the model? Okay. So we in the multiple regression, you put in salary as the outcome, all the other ones as predictors. And the first part of it is the model summary. So we get an R and R squared, and adjusted R squared, standard error of estimate. R squared change won't mean anything in this case because it's all one step. And then the significance level of that model and a Durbin-Watson. So you know what all those things mean?
17.3% of it.
Okay, so first thing is either the unadjusted would be the model as a whole, that is all the predictors against salary, accounts for 18.4% of the variance. If you adjust it for shrinkage, then you get down to 17.3%, just a small amount of shrinkage. Standard error of the estimate doesn't tell us too much by itself. That's the standard deviation of the residuals. And we can look at the significance, which means the model, we know the R squared is different from 0. So we're very sure, less than 1% in 1,000 times would this come out by chance alone. And the Durbin-Watson is 2.057, so what did that tell us? Near 2, so it's very close to 2. So we had no issues with serial correlation, autocorrelation, independence of observation. Those are all the same thing. Okay, then it does the ANOVA on that F to C. That's where the significance comes from before. So it does the sum of squares regression over sum of squares residual to give us an F. And significance level of that F, that doesn't tell us anything more than the significance of the F change up above. So we're very sure that there's really a relationship. And he actually goes through and shows you the formula for the shrinkage. Adjusted R squared, 0.159. Where did we get that from? Oh, okay, so 3 predictors seem reasonable because this would easily detect a medium large effect. Overall, the model accounts for 18.4% of variance in salaries, a significant fit of the data. The adjusted R squared shows some shrinkage from the unadjusted value, indicating that the model may not generalize well. Actually, it's not very much shrinkage, I would say. You can also use Stein's formula to get, there's another formula for shrinkage, which is a little more conservative, which would also mean may not generalize well. Notice he spells generalize with an S because it's a Brit. And color with a U. Okay, so then, next thing we look at is the actual equation. So, can we actually write the regression equation from this?
Yes.
What would it be?
It would be y equals negative 16.89 as a constant plus 6.234 times x to the sub 1.
Which is age
Yeah.
plus, or is it negative, sorry. Negative
5.561.
Negative 5.61.
5.561.
561.
And that's quantitative time in the model, so X up to.
Number of years.
Minus 0.196. And that times the attractiveness rate.
Okay, so let's interpret those. So that means for every 1 year of age, salary goes up by 6.23. I don't know how they actually measured salary here. It tells what the scale was, did they? Whatever those units are for salary, it can't be $6. So for every year older you are, your salary goes up. Years in modeling, the more years you model, your salary goes down. For every 1 year you model more, salary goes down by 5.61. Seems sort of counterintuitive to this one. And the more attractive you are, the lower your salary. That is, 1 unit increase in attractiveness lowers your salary by 0.196 units. But remember, that's with age and years held constant. Right, and this one's with age and attractiveness held constant. This one is with years and attractiveness held constant. So we have to think about those. Now, can we interpret those? So if we look at the actual formula here, we see that the amount of batteries. We see that the constant is significant. That just means that the y-intercept is different from 0. It doesn't tell us much here. That means if they were 0 years of age and had no years of modeling and no attractiveness, they would have minus 60 salary, probably in thousands. So we don't care about that one. For age, we can see that is significant. For number of years is significant, but attractiveness is not significant. So once you've controlled for, so they don't give us the actual correlations, do they? But if we knew those correlations, we could see whether attractiveness by itself was a predictor, and then what happens is if you take away age and number of years, maybe it goes away. Those are the B weights you gave us. The beta weights mean that we can compare them directly to one another. We can see that age is almost twice as important as number of years modeling. Even though it's a negative number, it doesn't matter. Gives us the confidence interval, the tolerance. So what does that tell us? Those are very low tolerance numbers, right? Remember, tolerance is 1 minus the r squared if that variable is the outcome versus the other variables as predictors. So tolerance is 1 minus the r squared if you did a regression. Let's do one with age as the outcome, and number of years as a model, and attractiveness as the two predictors. You would get about 92% variance accounted for by those two. That means the predictors are predicting each other. Not good. So those are very low tolerances for those two. Attractiveness is quite high. Remember, we want high tolerance, not low tolerance.
But with high tolerance, then the predictors are not as correlated.
Exactly. High tolerance means the predictors don't predict each other very well. So he just printed out the same thing here, I guess. He didn't give us squared semi-partials, which we should get, which would give us the unique contribution of each variable. But let's see what he says. It seems as though the salaries are significantly predicted by age of the model. This is a positive relationship. Look at the sign of the beta, indicating that as age increases, salaries increase too. Number of years spent as a model also seems to significantly predict salaries, but this is a negative relationship, indicating the more years you spend as a model, lower your salary. This finding seems very counterintuitive, but it will come back to that later. Finally, the attractiveness of the model doesn't seem to predict salaries. Next part of the question is whether the model is valid. So what they do is do collinear. He asked for collinear diagnostics and case-wise diagnostics, and he did a dependent variable histogram. You can see some positive skew there. So it looks like we might have a supermodel in the group here that may have messed things up. The normal plot doesn't follow the line really well. That may be a problem. Here's the actual scatter plot with, he uses standardized predicted values. I like to use unstandardized predicted values because they make more sense intuitively. Same basic pattern. You can see there isn't a great scatter plot for homoscedasticity here, right? And then he just did a salary plot of comparing age to salary. And looks like there's a slight positive relationship, but not very good homoscedasticity there either. This is years as a model versus salary. That's attractiveness versus salary. Now those are not partial. Yeah, those are partial plots with the other ones being held constant. So we ask for partial plots. See where it says partial regression plot, that means that's the scatter plot holding constant the other variables. It's not the straight scatter plot you get without holding constant. So there are 6 cases that have there's 6 cases that has a standardized residual greater than 3, and 2 of these are fairly substantial, case 5 and 135. We got that from here. Those big actual residuals. We have 5.19% of the cases with standardized residuals above 2, so that's as we expect. But 3% of the cases with residuals above 2.5, we'd only expect 1%. Because z-scores, 2.5 would be a 1% z-score, 2 would be a 95% z-score. Possible outliers. Normality of the errors. Histogram reveals a skewed distribution indicating that the normality of errors assumption has been broken. The normal PP plot verifies this because the dotted line deviates considerably from the straight line, which indicates what you'd get from the normally distributed errors. Not a random pattern, as we say, distinct funneling indicating heteroscedasticity. However, the Durbin-Watson does not fall within Field's recommended boundaries of 1 to 3, which suggests the errors are reasonably independent. Multicollinearity for the age and experience variable in the model, the VIF, are above 10, or alternatively the tolerance below 0.2, indicating multicollinearity. These 2 variables are measuring very similar things. Of course, this makes perfect sense because the older the model is, the more years she would have spent modeling. So it's fairly stupid to measure both of these things. This also explains the weird result that the number of years spent modeling negatively predicts salary. In fact, if you do the simple regressions with experience as the only predictor of the salary, you'll find that it has the expected positive relationship. You should have done those first, actually. Look at your irregular univariates first. All in all, several assumptions have not been met. So, and he gives a second problem. I think it's a little more valid one. I forgot what it is exactly. Shoot. It's in another chapter. Anyway, we see the R squares, about 8%, which is still significant. Durbin Watson's a little less than 1, but not too terrible. The Donald 1, no affiliation versus Krusty, no affiliation versus, I forgot what these are. He's got some ridiculous example here. Okay, I forgot to look at the book and see what it is. Here you got significance in 3 of the variables. Tolerance levels are good for all of them. So it's going to be a more valid model. Case-wise diagnostics, very small residuals, that's good. Nice normal curve, change in hygiene over the something or other. Something to do with the clown on this one, I think. Nice normal plot. Dependent variable change in hygiene. So here he's got a dummy code variable, so then you don't get good scatter plots in those because it's just 2 values. So these are all kind of done that way. You can probably read this for yourself and see. Okay, any other questions on squared semi-partially? Didn't cover, but we know what that is, right? Unique variance with everything else held constant. Look at your lists, see if there's any other concepts on regression you want me to cover. I don't have one of these for mediation moderation, so we have to do that on our own in a second. Going once, going twice. Okay, let's do one more and then we'll take a break. Let's do the bottom concepts. Anybody need to go over any of those? Path diagram, causal arrows, direct effect, indirect effect, interaction, moderator, mediator, Sobel, preacher, test of mediation. Okay, guess we got our break sooner.
Was the cost on those 2 pages? Oh, we each only got one.
You only got 1 page? Oh. That was my initial one. You guys got the 1 page.
I came back as she was the way it worked out, I guess.
I have no idea where it is continuing. It's all articles. Because when I look at the things, it looks like it's jumping. Holiday. I think it is.
Yeah.
So that's- From the last exam, which ones are the new ones? Is this, we already did all this, right?
Yeah, we haven't been tested on Manova yet.
Okay, so this is new. this-
Mancova, I think all that we,
Well, we did that, I think.
yeah, we did that. Do we do logistic? Yeah, we did logistic.
We did logistic list.
Yeah, so the only thing new, I think, is Manova. And discriminant, we didn't do discriminant yet.
Okay. We didn't?
I don't think so.
Okay.
I don't think we did.
I thought we did.
The last test we had discriminant output, I don't think so.
Okay. Then I know what to focus on more for this
Yeah.
one.
Any way to tell how I'm doing?
How are we doing?
Yeah, like in the course overall.
I don't have the grade book here. You can come look,
Okay.
so you know what your tests are.
I got 92, 88, 92, and then 84. And then, I don't know if today's decision tree was a double.
Decision trees don't
Doing
matter.
so well, and then I missed today.
Decision trees don't matter.
Okay,
Points are trivial.
I was stressing out.
So, yeah, so what does that average out to? If you average those, probably high 80, somewhere high 80.
I think I'm an 89. But you need a 92 and an A minus, is that right?
If you get above 90, your overall, you get a lot more overall points from homework, project, decision tree.
Okay,
So your overall percentage will be way above 90 if you get a 90 on the concept list.
okay.
So then if that's the case, then it's close to my minus probably 91 or 90 will get you to the minus.
So I-
Especially, yeah, so I mean, if you,
So getting an A on this final.
yeah, if you get the final, the cumulative final, not the decision tree part.
Right.
The decision tree part would help, but the cumulative final, if you can get something like a 90 on that, because it's double points,
Okay.
that'll put you over 90. Then you'll almost certainly get it.
Okay. All right, that's what I need to know. Thank you. Oh, that's what I wanted to ask you. I know that you think that I'm jumping the gun on the dissertation, but I talked to a gentleman yesterday, Dr. Eric Beckett. I don't know if you know him, he's the director of research.
Time for the time for
And,
So let's,
GETKA, he told me he was,
They do too, because there's
he's been a community psychologist as long as they've been making boats out of wood. Funny guy.
Okay, did you look and see it published?
I didn't look him up, I just had a wonderful opportunity to talk to him. And he seemed to know who I was on the phone. Because I guess he's in charge of the whole HPSP program.
Oh, I see.
Yeah. And,
I mean, it's fresh in your mind.
yeah, I guess I looked out and talked to him. And he said, well, you're on the right track. And he told me what I'm doing with my career. He said, the thing that really matters is getting your dissertation done. He's like, we want to see that. That out of anything is the most important thing.
Good feedback, good.
And I said, well, does it matter what you do it on? And I said, what about suicidality in the veteran population? He says, that's wonderful. He said, there's a ton of research being funded for that right now. That would really look good. And if you were to, unfortunately, not make it for the HPSP program, that, you know, if you were to say that you already turned in your proposal by the end of your, I guess it's the summer, prior to my 4th year, if you were done with that, you collected your data, and then you're well on your way. So my question is, I've got all these different people kind of giving me different ideas, but given that I want to get it done, and I just want to graduate.
Never say that again. That's always a kiss of death.
Is it?
Everybody wants to graduate, so it doesn't.
But I don't want to do, I guess that my point is I don't want to take on this laborious
It
project.
doesn't matter. You take on something you're passionate about, you're interested in,
Right.
and you do the best you can.
So I'm wondering if a measurement project coming up with a scale, since there is not anything really great out there.
Or isn't suicidality?
No, I saw a few, and one that's hotly used right now requires the veteran or active duty service member to actually assess themselves as either having generalized anxiety disorder or depression or PTSD. And how can a layperson possibly have knowledge to accurately do that?
Right. We talked to Dr. Mono about it.
Okay.
But, you know, you're going to need some sort of validity.
Okay.
It can't just be reliable. It has to be, to really make a dissertation, you have to give some sort of validity. That means you're going to need a military sample or somebody. I mean, I don't know how he would, what you really want is to follow people and see who actually attempts suicide. But that's not going to be easy to get. But possibly there's some group that would like to test out your scale. It doesn't really, they don't have to actually commit suicide, it would just have to be some other criteria for suicidal behavior.
Well, what about the national, there's like a national database that I know has all of that data on it. I don't know if I can get
Can't come up
access
with a
to
new
it.
scale on that, you're coming up, you have to put your scale on the database.
Okay, and then collect it from that
Yeah,
point, okay,
that would work.
great.
But anyway, yeah, so a measurement is tonight, you should talk to
Mono,
Dr. Mono about that, she would be the one that would be interested in that.
okay,
And you'd have to brainstorm some ways of doing that. But in the meantime, you just should be reading about suicidality.